ML, or machine learning in EventTracker, our quest for anomalies. So machine learning is a substantially overhyped term these days. It means all sorts of things to all sorts of people. Maybe it means self-driving cars, or it means a computer program that plays chess at a very high level. None of those things. We're in the log management business, and so therefore we're referring really to unsupervised machine learning, more specifically as it applies to time series. Log data is inevitably bound up with time, and so our machine learning is all about detecting anomalies within that time series data. This is a result of 3 or more years of development here at EventTracker. And for those of you that had earlier versions, V8, V7, we used to refer to this as behavior. For those of you in the UK, yes, there is a U there, but I am speaking to you from America, so it's behavior. And the whole design has been one that makes it very simple for the junior analyst to use and benefit from. Of course, if you happen to be a power user, then you can extend machine learning and its jobs as part of EventTracker in all sorts of interesting ways. So what problem are we seeking to solve with machine learning? Well, log data or machine data is being ingested by EventTracker in really large volumes. And we have to think about how to solve the known unknown problem. Right? What is the known unknown problem, by the way? It's the fact that there are certain conditions that we know to be problematic, but then given the very large volume of data, it's difficult to know or to be on top of when it is that these conditions might occur. Now, anomalies, or out of ordinary as we used to call it, observations can be a leading indicator of trouble. But again, that extremely large volume makes it impossible to touch in any kind of manual way. And then the static alerting that we had as part of EventTracker from version 1 winds up being insufficient. It doesn't adapt to new models in the data. It doesn't think about seasonality. It's so rigid that it tends to be sometimes more trouble than it's worth. And so therefore, machine learning becomes interesting. How do we do machine learning anyway? It's done by jobs. These jobs are defined by us at the factory or by you if you're a power user, and they operate constantly in the background. What do? Well, they look at the log data that's coming in via the data feeds, and they look for or detect anomalies in order to bring this to the attention of the analyst. So, hey, Mr. Analyst, wake up. Here's something unusual going on in this data feed that we see. You should probably investigate it and check it out. The analyst can then explore these anomalies and then find out what the factors are that influence the reporting of such anomalies. Why do we do all this? Well, obviously, knowing that we have a problem somewhere is a fine thing, but being able to understand specifically why it has occurred and what's influencing it is, of course, orders of magnitude better. Now, the machine learning implementation in EventTracker is self-learning. Remember we said a junior analyst can benefit from it? Yeah, so the user, as you may well be one, don't need to specify these algorithms. You certainly don't need to curate any of this stuff. You don't need to bother adjusting these machine learning models or some, obscure data science property in order to get the benefit of it. As new data is ingested by EventTracker, the machine learning models that we define will actually adapt themselves. Why is this important? Well, because data feeds have seasonality. What does that mean? Well, data looks different maybe over the weekend than it does over the weekday, maybe after hours than it does during hours, maybe over the spring versus the summer. And so the self-learning is important in order to be adaptive to the fact that what's normal, what's ordinary, what's routine might in fact be changing over time and not be static. That's one of the reasons those static alerts don't really quite work well. At the end of the day, machine learning populates these things called models. And what is a model? It's a self-contained artifact. In our case, it happens to be schema in a table. What do they contain? They contain historic information in a condensed fashion as to what's happened around a particular anomaly. What's valuable about this is that in order to access and explore, if you will, this model, you don't need to go back and look at the raw data and re-index it in any way. These models also evolve up to the last bucket, and we'll learn soon what the concept of a bucket is. And they're adaptive. So as they see seasonality, as they see changes, you can see what the differences are and what we consider to be an anomaly. So if you're going to be working with EventTracker's machine learning, it's time to learn some concepts. And these are very common concepts when we're using same terminology as we'll get in the industry, particularly from the Elasticsearch people. So let's look at some of these terms. A data feed. What's a data feed? Well, it's nothing more than a source of log or machine data. For instance, syslog streams are data feeds, as are data coming in from our Windows sensor, from our SNMP V1, V2, or V3 receivers, from Office 365, from VMware, from files that we might be receiving to process, and so on. So data feeds can be both real-time, as syslog and the Windows sensor will give you, and they can be batched. That is, they can be an IIS W3C file or a log file that's delivered to us maybe once a day. So these are all data feeds. Next concept, machine learning job. What's a job? Well, a job is what looks at that data feed, and then after matching and extracting and processing the data, populates something called a machine learning model. It is this model that ultimately drives the display that you see in EventTracker, and also the alerting. Hey, Mr. Analyst, wake up. Something unusual has happened. We're getting a lot of hits from this particular IP address to our website would be an example of a job output. Anomalies. Well, Webster says an anomaly is something that deviates from what is standard, normal, or expected. So how do we define anomalies? Well, we extract specific fields via the machine learning job, and then look at the frequency of occurrence. How often has this happened? To compare against thresholds and to report an anomaly. Hey, Mr. Analyst, wake up. We see that there are too many account lockouts occurring in the enterprise, much more so, maybe 50% more so than what is normal given what we have learned over the last 2 weeks. That would be an example of an anomaly. An influencer. So when we extract fields in the machine learning jobs, in order to identify an anomaly, an influencer is something that is the value of this extracted field. Let's take an example. Let's say we're getting a lot of login failures that are occurring, and they're occurring primarily because two particular accounts are failing all the time. One's a service account and the other is a user account. One's being actively exploited by some sort of hacking job, and the other has had a failed password, an expired password, and is continually and constantly causing these login failures to occur. The influencer then in this case would be the username. One would be the service account that's failing because the password's expired. The other would be the user that is getting hacked, as an example. So these two influencers might cause an anomaly as it relates to number of login failures that are occurring in the enterprise. And then we have this bucket and bucket span. These are important concepts, folks. A bucket is nothing more than a mechanism, a period of time by which we divide the continuous stream of data into batches for processing. We're getting data all the time from syslog, from Windows, from SNMP, from Office 365. By analyzing data in buckets, we can more easily see whether there have been any significant changes. And then we get the benefit of smoothing, right? Some of the random fluctuations get smoothed out. If you choose shorter bucket spans, when anomalies can be detected more quickly, and alerting, of course, can happen faster. But then you become kind of sensitive to variations or noise in the data, and you might get a lot of goofy, false positive kind of alerts. By the other side, choosing a very long bucket span can be a problem in that if there is an anomaly going on, it can get smoothed out, and also it might take longer for you to get the alert. Let's take a look. Here are, three bucket spans against the same data. You see a spike has occurred right there in the center, but then different bucket spans. At the topmost part of the chart, you have a 1-minute bucket span. What happens here is you can see the anomaly very clearly, that red line in the middle, but you can't quite see the periodic trend, right? So that's a little painful because it's interesting and useful to see the periodic trend. On the other hand, in the bottom chart, you can see the periodic trend pretty clearly, But then notice you can almost not see the anomaly. It doesn't seem to be much of an anomaly. It's the span in the middle, the 10-minute span, that tends to be the best for this particular sort of data. You can both see the anomaly right there in the middle, as well as you can see the trend pretty clearly. I remind you again that alerting is something that can get affected by the bucket span, and so selecting a bucket span is an important thing. Luckily for you, this is all done by us as part of the software. But if you're a power user and you're looking to define your own machine learning jobs, then bucket span is something that you should certainly pay attention to. So what's the anatomy of a machine learning job? We said jobs are the ones that run constantly in the background, and they ultimately populate a machine learning model with data. Well, they all have a name, and they have a bucket span, as we saw, that they operate with. They invariably use an anomaly detector. An anomaly detector in EventTracker is always a number. That is the frequency of occurrence. Now this number can either be specified, hey, if I ever see more than 10 logon failures in this bucket span, of 30 minutes, that's always a problem for me. You could specify that. Or you could say, there is seasonality. There are more students logging on in the fall and in the spring than there are in the summer and over the Christmas break. So then I don't want to specify a number like 3. Why don't you go learn? And whatever you learn is going to be the threshold. And an anomaly is if you get, a 50% variation above or below, if you like, the threshold. So this is an anomaly detector, and it's something that's part of a machine learning job. The job also has one or more matching rules, which it uses to identify entries in the data feed against which now it can apply these extraction and analysis rules to extract the relevant fields, thereby apply the anomaly detector. In the example that we just saw, you might look at logon successes or logon failures rather, and then identify the username as being the field and the frequency of occurrence of the total number of logon failures in a bucket span, and the influencer would be the username. 2 kinds of jobs are supported, single metric and multi-metric. In single metric, you consider only one field for anomaly detection. For example, how many total HTTP requests have I got? I don't care if they're gets or they're posts or they're anything else. I just want to know the total number. And then that total number is what I'm using to decide whether I have an anomaly, yay, nay. You also have multi-metric jobs, which consider more than one field for anomaly detection. An example is user location affinity. I am worried that a user might actually log in to a location or a target machine which he has never logged in before. So if Susan constantly logs into workstation 5, why then that's okay. We learned that behavior is normal. And one fine day, if she's suddenly logging into SQL Server 6, which she never did before, and so multi-metric, the user, Susan, and the location, SQL Server 6, that combination is considered to be an anomaly, and that's a multi-metric job for you. Here's how machine learning works. You define a machine learning job, and then you activate it. As part of the machine learning job, there is the definition of a bucket span, let's say 60 minutes. There are matching rules. So the job then runs constantly, looks at the data feed in question and says, do I have entries in this data feed that match the rule? Yes. In the example we're taking, we're going to say the data feed is coming from, say, an Active Directory machine via our sensor, and the matching rule is to look for Windows login failures. In a 2008 domain, this would be easy. You get events of ID 4625, and so that would be the matching rule, right? In the real-time feed coming from the Active Directory machine, look at all of the data. If the event ID is 4625, why then you have a match, and that's something I'm interested in. So then, now that I've found it, a 4625, what am I looking for? Well, I'm using an extraction rule to identify the field of interest. Who is the one that's failing to log in? Okay, so that's the username. And we can surely find that pretty easily because all 2008 R2 and higher have, those nice XML representations. So finding the username that failed to log in is an easy thing. We now can apply the anomaly detector in the bucket. As we're processing it, let's say it's a 60-minute bucket. How many of these login failures have we observed? because each time we're getting a login failure, regardless of who the user is, we're incrementing the total. And so if we're saying that normal number of login failures for this organization, as we learned over the seasonality, is say 3 in a bucket span of 60 minutes, why then have we seen more than 3? And if we did, how much more than 3? Let's say that our variation setting was 50%. So we needed to see maybe 5. And if you see 5 login failures in 60 minutes, why then you have an anomaly. So now you must populate the model with data for visualization and then issue an alert if such an alert is configured, saying either I'm seeing an anomaly, hey, I've seen 5 login failures where I normally see 3, or I might also have a login failure for something first time seen, that is, I'm seeing user Joan login, fail login for the very first time, never saw her fail login before. That's a problem. So what's new in version 9.1? After all, if machine learning was called behavior and was available in version 8 and earlier, what's new in 9.1? Well, the big thing is, in versions prior to 9.0, machine learning was only available on an instance basis. For those of you that are Essentials customers, what that means is it was only available to the master MSP. In 9.1, machine learning is now available on a group basis. That is to say, it is available to the sub-MSP and quite possibly to end customers as well. That's a big deal in version 9.1. Also worth noting, for those customers, particularly enterprise customers that are using the collection point collection master model, the machine learning components that are being provided fully support that model. So we can roll up for enterprise customers either on an instance basis if you're selecting the old style of working, or on a group basis if you want to enable that functionality. We provide a variety of machine learning models with Essentials for all sorts of Windows events, including the ones that you see: software install, USB, Windows logon, IP address, location affinity, logon failure. And the idea here is to be able to detect all of these anomalies and then report them on a group basis. If you are a enterprise customer, why then you not only have these 7 models, but pretty much anything that our team can concoct for you across many products, not just Windows, and across all sorts of data feeds, including SNMP, including syslog, and pretty much anything else. We're releasing machine learning, or re-releasing machine learning then. And in which versions might it be available? Well, it's available in 9.1 and higher. It is available to you if you are a EventTracker Security Center, that is to say a license-only buyer. So if you're a self-serve buyer that purchased the software and are operating it yourself, if you are in maintenance, you can get machine learning by upgrading to 9.1, and there is no additional cost. If you're a service customer, maybe you've selected EventTracker Symphonic or Symphonic Enterprise, you can choose to get this implemented for you by the ECC on either an instance basis or on a group basis. There is no additional cost since you're already having the subscription for EventTracker. Of course, your instance must get upgraded to 9.1 to get this, but there is no license fee. If you're a Symphonic Essentials or an EventTracker Essentials customer, and this is the most exciting of all news, you can now get it implemented on your instance. Of course, you must upgrade your instance to 9.1 on a group basis. That is to say, it can be multi-tenanted and apply the rules independently for each of your sub-customers. Since you are in maintenance, if you have the EventTracker Essential services, there is no additional cost to you either. So let me demonstrate how machine learning actually works, and we'll take a look at a job, its definitions, the overall settings for machine learning, including enabling it or disabling it. We will walk through a model and explore what that model has to offer using the Model Explorer, how an analyst can pivot from that information to search, and then of course add it to a case so that we can co-manage this for you between our team and yours if you happen to subscribe to the service. Okay, so now that we've gone over the terminology of machine learning, let's take a look at machine learning in practice. What I have in front of me is an instance of EventTracker where machine learning has been enabled in the multi-tenant mode. So if you happen to be an administrator, you can see the jobs that have been enabled as well as the settings that apply to the machine learning example. In particular, the machine learning job that I want to focus on is one that learns about USBs. So USBs are prolific in the medium enterprise and the small enterprise, and they're very good for productivity. Unfortunately, they can be a source of information leakage as well. So we have a rule for machine learning for USB, which basically learns about these devices as they're plugged in, identifies them by their serial number, and can tell you when there are either the first time seen or an anomalous behavior. And this actually has happened. Now, by the way, this is the multi-tenant version of machine learning. This is a MSP here that has multiple customers, and each of those have their own separate environments. And if I look at one of them, for example, Acme, I'll see a set of alerts. But if I look at another one of them, say for example McDowell's, I might see a completely different set of alerts. And this is the multi-tenant instance. So I'm back to Acme, and the thing that I see is there has been a first time seen USB. If I try and expand the details, what I understand here is that this has happened on workstation 1, at 6:21 this morning, and it happens to be some user by the name of Anderson. This is the serial number, begins with a 4, ends with a 4, and the volume label is personal, so this isn't something that was issued by the company. And because it's first time seen, this is something that raises my hackles as an analyst. This is something that a Symphonic Essentials analyst would do. Well, then it's time to explore the model. So let's run over to the machine learning part and focus on USB activities specifically for this customer called Acme. And what we see, the yellow part begins with a 4, ends with a 4. And so clicking on this allows us to get to the model explorer for USB devices. And what do we see? We see that there is a first time seen or a rare USB of this particular serial number. Well, gee, I wonder what happened. And so I might decide to conduct a log search to identify what were the logs associated with this particular USB. And what we see is that it got plugged in at 6:15. And so USB monitoring started. The user was Anderson right here. And then it was pulled from the machine at 6:20 by Anderson. So if I expand the pulled event, the stopped event, and take a look, yes, it happened on workstation 1. It happened at 6:20. The user was Anderson. The volume label was personal. The volume serial number is this number here. And the surprising and disappointing thing is that payroll.xlsx got added to the USB. So when it was pulled, it contained information which was confidential to this particular company, to Acme. Now, this is an insider threat, where someone from the inside has done something that you really hope they don't do. Very difficult to catch with antivirus or even with EDR, and certainly nothing to do with the firewall because it doesn't touch the perimeter at all. So if you're interested in exploring other activities of this user Anderson, why then you can click on it and you can see that he logged in successfully at 6:14. He plugs in the new device, the USB, at 6:15. Some stuff happens in between, and then at 6:20 he pulls the device, and then sometime later, 2 minutes later, he clears the audit log. Right? This is a very troubling activity because you almost never clear the audit log. This person has done so, and then of course he kind of logs off. So if you look at all these activities, it begs the question, what was happening on Acme Workstation 1? So click there in order to identify around 6 o'clock, 6:15 thereabouts. Well, what we see is that there was a logon that happened at 6:12, 2 minutes before, 6:13. And this was from some user called Kenneth, right? So he was active on the system. And right after that, you see that Anderson logged on at 6:14, plugs in the new device at 6:15, pulls the USB at 6:20, logs off, clears the audit logs, and so on. So then who is this Kenneth guy and why is he involved on this machine would be a question. All right, pivot to Kenneth. And what we see here is Kenneth logs on at 6:10. He creates an account. Well, what account did he create at 6:10? Oh, he created Anderson. All right, so the picture is becoming a little bit more clear now. 1 minute later, he adds Anderson to the administrators group. Here's Anderson being added to the administrators group. Well, this is getting more and more difficult. 1 minute later, there is an attempt to plug in a USB. That attempt is disabled by EventTracker because it's not in the policy for the domain controllers to allow personal devices. And so then what does he do? He logs off as Kenneth. And you know the activity from 6:14 onward. That same personal USB is taken over to Acme Workstation 1 as though it's done by Anderson. Payroll.xlsx is put onto it. And finally, that sequence ends at about 6:20. At 6:24, what we see is Kenneth is back on again on the domain controller. And now he's deleting the account. What account did he delete? Well, he deleted the account called Anderson. And then a minute later, he has cleared the audit log on the domain controller. So this is obvious what's going on now. Kenneth is in fact the bad guy. He's got admin privs inside Acme. In order to cover his tracks, he's tried to make a user called Anderson. And he's tried to do activities as Anderson, and then he's deleted the user. He's tried to clear up his logs. Of course, this doesn't matter in EventTracker Essentials because the moment the log is written on the machine, it is securely transported away to the EventTracker instance at our data center in Houston. So he can clear logs all he likes. It's really not going to help him out. Now, when the analyst discovers all this, why then the first thing he's going to do is create a case in the casebook. And the case here would provide detail as to all of the things that have occurred. So here is the case that has been created. And as you can see, there are documentation saying that a rare USB device, Anderson, was logged in and the request is to investigate. Now, another advantage of EventTracker 9.1 is our integration with ConnectWise Manage. So if the MSP in question here that is benefiting from this multi-tenant machine learning happen to also be a ConnectWise Manage user, why then you can integrate cases that are opened in EventTracker by our SOC team with tickets in ConnectWise. So the moment we open a case down in EventTracker, why a ticket can be caused to be open in ConnectWise Manage. The MSP's technicians then would only have to sit in Manage and not have to worry about notifications in some other manner. Now you recall that the company that in question being managed by this MSP was Acme. So if I look for Acme, I would find that yes, there is an Acme Corp and there is a ticket associated with it by the number 855. And if I click on this, I can get to the details of the ticket, and you can see that this is that ticket which was opened down in EventTracker. It says it's a rare personal USB detected by user Anderson. This is our analyst informing you and requesting that you please investigate. Well, as the technician, you can decide that it's assigned and responded and change the status, and then begin investigating this incident. You can add notes in ConnectWise Manage saying that you're contacting Acme Corp, and you confirm that this is a problem, you've escalated it, and you thank the EventTracker team. Now, if you've resolved this, why then you can say, or you can say something like, I'm the tech, I've picked up this ticket, and so now I have decided that this is in progress because I'm in the process of investigating it. The EventTracker casebook has two-way integration. And so you having made the change to in progress assigned as the status of the ticket in the EventTracker instance has also been updated. And so this is a very nice method by which EventTracker's SOC and the customer, the MSP's instance of ticketing can work together. So what did we see here? We saw machine learning in action. We saw a set of rules. We saw an insider threat where somebody called Kenneth decided to abuse the system. And it was caught because there was out of ordinary or anomalous behavior. First time we had seen ever that USB. So this is an exciting new addition to the EventTracker Essentials capabilities. Notice that it's multi-tenant so that Acme can have one set of rules or models, and McDowell's or some other customer can have a completely different set of behavior, and the model faithfully follows along with the permissions. So you as the MSP can see everybody that of your customers, but if you provided your customers with access, why they could only see those data for themselves. So not only is machine learning multi-tenant, but it is also highly capable, and without any effort on the part of the user, that is no data science knowledge, no adjusting the properties. The model learns itself and is very efficient, runs 24/7. So this happened at 6 a.m. Didn't matter. All of the data was caught, and the 24/7 service that the Symphonic Essentials team provides would alert you in your preferred method. In this case, it was ConnectWise as a ticket, and so that's the way it was. But thank you for your attention. Have a good day.